welcome. Today we're going to be looking at the unit test for matrices, one of the topics on Precalculus. As always, we're going to be going through this entire unit test to help you understand how to approach and solve these questions on matrices. With that, let's get started on our first question. Let's go. So we are given four matrices total, two sets of them, and we're asked which of the following calculations are possible. And we're given addition and subtraction as our operations. But you can only add and subtract matrices that have the same dimensions, right? So A and C have the same dimensions, right? 1 by 3. And B and D also have the same dimensions, so 2 by 2. So anything A and C you can do. A and C, C minus A. Anything with B and D you can do. D minus B. Everything else is, well, the only other one is B plus C, which you can't do since they have different dimensions. So these are our answers, and we can move on to the next question. All right. This matrix represents the number of direct public transportation routes, either bus or train, between three different cities, where rows are starting points and columns are endpoints. So you have start/end, city 1, city 2, city 3 for start and end. Which city has the most incoming direct public transportation route? Well, let's think about this, right? City 1, if we look at city 1 to end, that means that there's seven routes coming into city 1, right? For city 2, there are 11 total, so there's 11 routes coming into city 2. And for city 3, there are 8 routes coming into city 3. All right, so that means that city 2 has the most incoming direct public transportation. It's the most routes to it, the most routes that are ending in city 2. So that's our answer. Let's keep going. Consider the following matrix. If this was the coefficient matrix of a system of two equations, the system would look like this. We're going to rewrite each equation in the system in slope-intercept form. Complete the statement relating the number of solutions in the system to the invertibility of the matrix that represents it. System has exactly one solution, right? If you set the y's equal, then these have different x's, so you're going to have one solution. The matrix is going to have an inverse if it has one solution. Okay, because that means what that means is that the x's are not the same, right? So if you had no solutions or infinite solutions, then you might have some trouble. Here you do have an inverse because there's only one solution, right? It's a pretty generic, basic matrix, so you're going to have an inverse, and that's our answer. Let's keep going. Instead of the systems of equations, the system can be represented by the following matrix equation, where A is a 3 by 3 matrix and B is a 3D vector. Okay. See, in this scenario, it might help to have a little bit of context on what this A times this vector or slash matrix is. Okay, so now when you're multiplying two matrices, you use the dot product. The usual way we do it is the dot product. And what that means is that here you would take this first row on A and multiply this one right here by this x, the one right here by y, and the one right here by z, and you'd add that up, and that would give you what this is, this first one, right? So if I wrote 1, -2, and then 3, and I wrote 6 right there, what would that mean? Well, it means that when I multiply this part by this vector, then I get the 1. So x times 1, x, minus 2y, plus 3z, and that's going to equal 6. So that equals 6. So we're going to do the same thing for the other ones. We have -4, we have 5y, and then -6z. Here we have 8. And then here we're going to have 7, -8, and 9. And here we're going to have 1. And those are our two matrices. So let's keep going. Gustav was given the following equation. A times vector x equals vector b. A is an invertible n by n coefficient matrix. X is an n-dimensional vector. B is an n-dimensional vector. That's how we solved. Let's see. So the inverse, so we multiply both sides by the inverse of A. Okay, you multiply by the inverse of A. And then we have what? Okay, so multiply both sides by the inverse of A, and then we have a to the negative 1 times a, that is going to give you a matrix that looks like something like this. 1, 1, 1, 1. It's going to go diagonal like this. And everything else is going to be zeros all around here, everywhere. Just zeros. 0, 0, 0. So then you're going to multiply this by x, and you do get x, x. You do get this equals to x. So this is equal to x. Multiply both sides, that's it. You can specify whether it's a inverse of a times dot x, or inverse of a dot a times x. That is a very good point. He didn't specify that. And then since we know that the dot product, right, we know that the dot product is going to be it's going to be in different orders. You multiply both sides by a1, you have to do that in the same order first off. He didn't specify this. This is not an issue really, and this is equal to x. So our answer is B. That is our issue. Let's keep going. Consider this matrix transformation and it's performed on the following rectangle. What is the area of the image of the rectangle under this transformation? Alright, so let's start this down. So I have a notebook here, so I'm going to be writing on. Show it to you. Alright, so we have the length is 9, the height is 4, so 9 times 4 is 36. That's the area right now. Now the area at the end is going to be related to the determinant. The determinant of a matrix, and recall that determinant of a matrix ABCD is going to be AD minus BC. Alright, so this is what I mean. Alright, so you have this kind of matrix, and this is the determinant, and then this is just the area that I wrote down. Now, the determinant here, since we have a matrix 5, 10, negative 8, 4, is going to be 20 minus negative 80, or 100. And now we multiply this 36 that we had by the determinant, and we get 3600. And that is our new area. Alright, that is the area of the new rectangle. So 3600. Let's keep going. Right, matrix A represents the number of weekday direct train routes between 3 cities, where rows are starting points and columns are endpoints. Alright, so we have start slash end, city 1, city 2, city 3 for both of them. Over the weekend, the number of train routes between each pair of cities is cut in half. Matrix B represents the number of weekend direct train routes between the city. Complete matrix B. So we're just dividing everything by 2. So for here and here we have 8, so it's 4 now. Then there's 6, so it's 3 here. That's 2, so 1, 0, 0, 10 becomes 5. We just divided every single thing by 2. That's all we did. So now we have a matrix transformation just like that. So let's see. So we have 2 minus 1, 1, 3. And we're applying that with vector 2, 3. Now recall how the dot product works, right? So we have this written out, this equation right for 8. Recall how the dot product works. You take these two numbers and you transpose it onto here. Or you could take these two and transpose it onto here. Right? So this 2 goes with that 2, this negative 1 goes with the 3, and you get 4, 2 times 2, minus 3, negative 1 times 3. So 4 minus 3, that's going to be 1 here. And then you do it with the 2, or sorry, yeah, then you do it with the 2, with the second row. So that's going to be the 2, 3 on this 2, 3 onto this 1, 3. So 2 times 1, 2, 3 times 3, 9, and that becomes 11. It becomes 11. All right, 111. That is our answer. 111. That's the image of 2, 3 under the transformation. Let's keep going. Find the values of x and y in the following scalar multiplication. Well, scalar multiplication is pretty basic, right? You're just multiplying each term by that. So negative 1/3 times x negative 9 is going to be it's going to end up with negative 1/3 x Negative 1/3 times negative 9 is going to be 3. So we have negative 1/3 x3 is going to equal 2y, which means that x is going to equal negative 6 and y is going to equal 3. At scalar multiplication, you don't have a dot product or anything complicated. You just multiply this by every single element. That's it. This is that. That's 3. Let's keep going. Consider this matrix. We want to find the inverse of this matrix. Okay, so we can go back and think about what the inverse means. So the inverse of A, we call this A, times the inverse of A to the negative 1, is going to equal a matrix. In this scenario, 2 by 2 matrix is going to equal a matrix that looks like this. It's going to equal a matrix that looks like that. Sorry, no it doesn't. I lied. That is not correct. It's going to equal a matrix that looks like this. I held it up and then realized I screwed up. It's going to look like this. Okay, the ones are going to be diagonal. So 1, 1. So first column, first row, and then a second column, second row. If it was 3-dimensional, third column, third row, and you get the point, on and on. But this is 2 by 2, so that's what it's going to be like. So we want to find the inverse, so like the A negative 1. So we could try a dot product and find systems of equations for that, but that seems a bit too cumbersome, a bit too tiresome, and there's a lot easier way to do this. Right, so we're going to define this as, say, a random matrix, A, B, C, D. And in this scenario, A is negative 4, B is 2, C is negative 6, D is 6. And the inverse of that, our formula that we have, our inverse, is going to be that this is nothing but 1 over the determinant, AD minus BC, times D. And so D is going to be where A was, negative B in the place of B, negative C in the place of C, and A. There. So it's going to look like this. Okay, this is the inverse of that. Okay, so now we just plug in negative 4, 2, negative 6, and 6. Right, so the determinant here is going to be negative 24 minus negative 12, or negative 12 in all. It's going to be negative 1/12 times the D is going to be 6, negative B is going to be negative 2, negative C is going to be 6, and A is going to be negative 4. I'll multiply all that by negative 1 over 12, and you get negative 1/2, 1/6, negative 1/2 again, and 1/3. And that is going to be it. Alright, that is our answer. That was this entire unit test on matrices, one of the topics in pre-calculus. If you like these videos or find them informative, please be sure to like and subscribe. With that, I will see you next time we continue going through our pre-calculus videos. Until then, I'll see you next time.